Hi, my name is Heidi, and in this video, I'll be explaining the particular antiderivatives topic. Which is also called PA for our Calculus 1 class. So, in this type of particular antiderivatives, we'll need to know this function. Integral of f of x times the derivative of x equals capital F of x plus c, where this part of the function, it's our general antiderivative. And this part as well represents the family of functions. And lastly, this plus c right here. It's very important to write this plus c in order to resolve for a particular antiderivative. This plus c represents the constant of integration that all integrative functions have at the end, the plus c. And in order to solve this plus c, you'll need to get initial conditions given in our function to get the c value for it to be found. So right now, some examples. So example 1. In this first example, we have that f derivative of x equals x potential 3 plus 2x plus 1. And we also know that f of 0 is 3. So to solve this antiderivative, and particular antiderivative function, we'll need to rewrite f of x equals the derivative of our function, which is x exponent 3 plus 2x plus 1 derivative of x. And right now we solve this integral where x exponent 3, it's x exponent 4 divided by 4 plus the derivative, the integral of 2x, it's 2x squared divided by 2, and the derivative, the integral of 1, it's x plus c. It's very important to write this plus c. And right here, we can cancel these 2's. So if in our problem, we know that f of 0 equals 3, we substitute this 0 in this x's of our function to find the c value. So this will look like 0 exponent 4 divided by 4 plus 0 squared plus 0 plus c equals 3. And if we solve for this, it's 0 plus 0 plus 0 plus c equals 3. So c equals 3. And lastly, our particular antiderivative function, it's easy to find. So we have that f of x equals x potential 4 divided by 4 plus x squared plus x plus, and in this particular antiderivative, instead of writing the c, we write what we got in the c. So plus 3. This will be our particular antiderivative solution. So that's all. Right now, another example for it to be a little bit more clear. So example 2. In this second example, we'll have different values. For f double derivative of x equals minus 32. And we know that f derivative of 0 equals 10, and that f of 0 equals 5. So we solve for this. So f derivative of x would be the integral of our second derivative, which is minus 32 d of x, which if we solve, it's minus 32x, because the integral of minus 32, it's minus 32x plus c. Don't remember the plus c. And if we know that f derivative of 0 equals 10, we solve for that. So minus 32 times 0 plus c equals 10. So 0 plus c equals 10. We know that c equals 10. And in this second exercise, we also have that f of 0 equals 5. So now we need to find the other integral, f of x, which is the integral of minus 32x plus 10 d of x. And if we solve for this, you'll get minus 16x squared plus 10x plus c, because the integral of minus 32x d of x, it's right here we have a 1. So in this integral, we need to add 1 to this 1. So it will result x squared. And this 2, we pass it at the beginning of this minus 32, but in a fraction way where you have 1 over 2 and the minus 32x squared. And this means minus 16x squared. And well, that was the explanation of the integral. And lastly, if we know that f of 0 equals 5, we solve for f of 0, where we'll need to substitute this x in our function by a 0. So we'll get minus 0 plus 0 plus c equals 5. So right here, we know that the c equals 5. And for particular solution, now it's easy to rewrite, because the particular solution, it's f of x minus 16x squared minus 10x plus, we write this c equals 5 instead of the c. And that will be it for this second and last problem. So that will be it for today. Thank you very much.